Welcome back to Matter and Meaning. This is episode number 9, and the guest joining us today is Dr. Nick Czapla. Nick is a Stanford scientist who completed his PhD at Ohio University. His past research was focused on relativistic plasma physics, specifically relativistically induced transparency. He did this through ultra-thin targets using Gaussian laser profiles. He has also worked at Aerojet Rocketdyne, a company who's provided propulsion systems for NASA's deep space exploration projects for decades. Nick helped design rockets for Aerojet using specific modeling techniques that he learned during his education. He then went on to work at SLAC on their laser systems. During the time of the recording of the episode, Nick was actually in the UK helping Rutherford design a new laser system that they are planning to use for research. There were a wide variety of interesting topics we discussed in this episode, so we hope you enjoy.
Nice. Okay. So we can just start whenever then.
Yeah, we'll just jump into it if you want to
Yeah.
talk about education first, I guess.
Yeah, sure.
Okay. You can
All right.
first question.
Yeah, okay, we're officially starting now.
Dig it.
Okay, sweet.
Love it.
So we saw that you did your undergrad in California, but then went and did your postdoctorate in Ohio State University.
Almost. I'm from California. I'm from San Francisco area.
Sure.
I did my undergrad at Cal Poly San Luis Obispo, which is about 3 hours south of San Francisco on the bay or on the water.
Okay.
And I very much didn't want a PhD. At 21, I was sort of over school and wanted to make money. And so I got a master's degree to sort of separate myself from the other bachelor's people. And so that took about a year and a half, something like that. And then I went into industry. And so then from there, I got living in La Jolla, which if you don't know, is sort of the heart of San Diego, very stereotypical San Diego. Lots of tan people, lots of sun, lots of beach, beautiful weather all the time. And that's when I was like, you know what? Let's move to Ohio. And that's where I went to get my PhD. So not a postdoctorate, but my PhD was in Ohio.
Yeah, I realized I misspoke
No,
there.
no, no,
Yeah.
no, it's fine. It's fine. I haven't
Um,
actually done a postdoc. Um,
okay.
I didn't want to do a postdoc either, because it's just more like hopping around, trying to find a group or a research that has money for you and your interests align and has time,
Yeah.
and it can be challenging. And I was sort of over that, so I went into industry again.
I've also heard, I don't know if this is true, but I've heard rumors about like, I don't know if I want to call them rumors either, but people are saying like, postdocs are basically just cheap work. I mean, if you
100%. Oh yeah, it's not a rumor. It's facts. Um,
Got it here first.
so, yeah. So I guess I don't know how much you want to jump into it, but right now I'm an associate scientist is the official title, but I'm effectively a laser scientist at SLAC, National Accelerator in the LCLS division, which is the linear coherent light source. It's their X-ray source. And I make them out of money, but there is a position called an RA, a research associate, which is technically one level below me, but for all intents and purposes has roughly speaking the same qualifications and makes, I don't know, half of what I make, maybe a little bit more. And design a postdoc, it's a little bit different in national labs in terms of the terminology and verbiage, but it's cheap labor, and it's unfortunate, but there's enough people who are willing to do it that it can be supported, which
Yeah.
is not great, but it is what it is.
Yeah. I was actually going to ask a little bit about that. What really
Sure.
is the difference between a associate scientist and a scientist in terms of do scientists just come in being a scientist without like a bunch of prior work behind them, or do you have to start off as an associate scientist and go up, or is it more of just like a salary thing, or
A little column A, a little column B. So I do work in a national lab,
yeah.
but it's a strange one in that the contract is given out from the DOE and is run by Stanford. So I'm a Stanford employee, but that therefore means I have to
Mm,
abide by the rankings and job titles associated by Stanford, as opposed to other national labs like Lawrence Berkeley National Lab or Lawrence Livermore National Lab, which are also in the Bay Area. So they're about 40 minutes away from where I work.
yeah.
But they have their own, not owned, but they're run by different organizations, so they have their own different job hierarchy. And I'm correct in saying that Stanford, or well, Slacks has the least amount of separation. There's only sort of the four steps. Um, but generally speaking, an associate scientist at Slack, anyways, is somewhere between 2 to 4 years after your PhD is where you are. And then given that you've earned your time, you can then be promoted to staff scientist. But it doesn't, if you had your PhD 10 years ago and were working at Berkeley National Labs or somewhere in the UK or somewhere else, you wouldn't have to start over and be an associate scientist. You could then just be a staff scientist or a senior scientist or lead scientist at SLAC. Um, so it's a little bit, it's just the job title. But there are pay differences between associate and then staff and lead and senior. Um,
Yeah, sure.
So it's
so yeah.
sort of a case of just working your way up, I guess.
Yeah. That's exactly what it is. It's not the most defined, in that if there's only it's not that there are only four titles, but basically there are only four titles, and that so it's a associate, then staff, then lead, and senior. And then the associate to staff is the most defined, and then it's usually this sort of like 2 to 4 year period. But staff to senior or to lead is much longer and much broader. You have to sort of become relevant, world-renowned in whatever area of research you're in. You have to publish not necessarily a specific number of papers, but just published in general and high impact stuff. And then if you get so the way LCLS works is that there's an X-ray source. It comes through and then it goes to 6 different instations, which we call hutches. Each one of them focuses on a different area of science. So I work at MEC. I'm the laser scientist for MEC, which is the matter and extreme conditions. We focus on plasma physics. Others focus on chemistry or biology, life science. And anyways, they're all separate groups that work with the X-ray source, but they're sort of their own individual team amongst LCLS. And then we work together in the broad sense to make LCLS better, but very much a lot of my day-to-day is spent with the MEC folk. And I don't necessarily see as much of the CXI folks or XCX folks, which I forget what they stand for, but we don't necessarily work that much together in our day-to-day goals where we might have weekly meetings instead. But anyways, each of those groups has like a lead scientist, and you can become a lead scientist before a senior scientist, or the promotion in that skill is a little bit different, and that's where you're not as tied to just the most senior number of people or senior years gets the lead. It doesn't always work that way. Some people don't want it because it might come with more responsibility, and more meetings. Some people don't like meetings. I myself am not the biggest meeting fan, but they happen. It's sort of a part of every job. So it depends on where you want to, or if you want to go to management, and be the head of I am at the laser scientist for MEC, but I am in the laser science SRD division, so science and research division, and so you can be a management in that route. And our manager has his own PhD in lasers and physics, but he went more management route to help out and help other people. Yeah.
Okay.
So you mentioned there's 6 different sort of categories or research areas that have
Yeah,
focused.
hutches.
Where-
Yeah.
Who sets them? Where do they come from?
So they come from on high at LCLS. So they're already established in that they've got their own lab room basically, and they each have their own or basically they each have their own laser source. And so then whatever the science is, so the MFX, which is, man, I am forgetting what they all stand for, but they each have their own laser source, but they'll be different types of lasers. So ours is MEC. We have the highest peak power and highest energy, and so what that means is that one of our lasers is a 100 joule, 10 nanosecond laser used mainly for warm dense matter, shock driving physics. And the other one is a 1 joule, 30 femtosecond second laser, and that's our high peak power laser, and that's used for more relativistic plasma physics, and higher levels of warm dense matter. But the other lasers at other hutches don't do anywhere near the level of energy we do, but they might have a higher repetition rate or a shorter pulse, and so they can access different kinds of science in that sense. So, like the XCS might look for crystallography and scattering off of various chemistry, liquid phase or gas phase chemistry that is induced by this sort of laser catalyst. And then the X-ray comes through and probes it, images it, scatters off of it, diffracts it, and then that's what makes LCLS so impressive. The lasers are great, sure, but I'm actually in the UK right now building an arguably more impressive laser than the laser I work at, but it doesn't have a giant X-ray source with it, and the X-ray source is huge, and so it can probe things that regular X-rays just can't, or regular lasers just can't get to.
So I was talking with somebody, well, we both know him. I was talking with Bob. He was talking about how it's actually quite uncommon for people to be in kind of the situation that you're in, where you're coming over here for a short period of time and doing some work on somebody else's lab and then going back. Um,
Yeah,
so
yeah, that
how
is.
did you get in this position, and Was this like
Um,
something offered to you that you took
a
up?
little column A, column B, in that it was so I work at LCLS at SLAC in general, and we're a part of DOE. And there's some level of sort of hierarchy of higher ups that do laser physics in general that communicate with folks in Germany and the European XFEL, which is sort of like a European version of SLAC. And then at RAL, which is the CLF Central Laser Facility here in the UK at Harwell campus. Anyways, there's this higher up of people that communicate, and they want to. There's this acknowledgement that we do things very well, they do different things very well, the Germans do different things very well, and there's not a real reason why we can't collaborate and exchange knowledge because it's hard to necessarily, in my opinion, it's hard to fully understand and learn new things unless you're there hands-on, getting your elbows dirty and all that. So the STFC, which is the Science Technology Foundation Center, it's something in the UK. It's sort of like the equivalent of a DOE. Uh, there's this acknowledgement that they want to collaborate and exchange knowledge with some folks at SLAC. And so I was sort of the first to be asked to come over and exchange knowledge and help them build their new EPAC laser, which is the Extreme Photonics Application Center laser. And in 6 to 8 months, they're going to send someone over to SLAC and do SLAC research for the MPC, which is the multi-pass cell, which is just the technique we've sort of worked on in terms of making lasers broader in the spectrum so you can make them shorter in time.
Interesting.
So it's sort of I was asked slash voluntold to come and help out and build, but I jumped at the chance because it's a great opportunity. I don't have a 50 joule laser back at SLAC, and so they're fun to work on. And so it's a good opportunity for me to just do more work.
Going back to your PhD,
Yeah.
we tried to read some of it, but as
You'd be the first.
yeah, so well, as we are with most of the PhDs that we try to look into for most of our
Nice.
guests, we did not
Very
really
cool.
understand it.
Yeah, that's fair.
So,
No, very fair.
so do you want to tell us a little bit about what relativistically induced transparency is, if you
Yeah.
can?
No problem at all. So MEC focuses generally on plasma physics, 1 minute matter. And plasma is this fourth state of matter. So you got your liquids, your gases, your solids, and then plasma, which you can generally think of as sort of a hot electron soup, hot ionized soup. And it's special in that you can compress it higher than you can compress solids. Solids sort of break down. You can heat it up higher than you can heat up. If you heat up a solid too much, it sort of melts. But you can heat it up even further and sort of make this plasma. If you go even further with the lasers that I used in grad school, which was a 300 terawatt or petawatt class laser, you can strip off the electrons from whatever the atom they're associated with. So if we look at copper, for example, it's a really classic target. You strip off the electrons, awesome. If you strip off enough of the electrons, you get this situation where you have what they call overcritical plasma density. And what that basically means is that your laser can go through and propagate through your plasma gas, so to speak, and just the way that laser can propagate through the air, no problem, until you get an electron density that is too high, and then your laser reflects off of it. It can't get through. It's too dense. Uh, okay, very cool. It's a very classic known for 800 nanometers, which is generally most high-SAF lasers. That is about 10 to the 21 electrons per centimeter cubed. The thing is, if you accelerate the electrons, if you energize them even more, what happens is that you can get this relativistic speed of the electron, which if you've taken your quantum, you'll know that generally speaking, your gamma from your relativistic factor attaches onto your mass. And so the way the electron density or the plasma frequency goes is that it's 1 over mass. If you now throw a gamma on front, basically what that means is if you accelerate your electrons so high, you can effectively reduce the electron mass and then reduce your critical density. And therefore you go from a situation where your density was so high that your lasers can't penetrate through to the point where now your laser is excited enough or can then transmit through only in this relativistic regime. So it's relativistically induced transparency because before it was too excited, it couldn't transmit through. Boom. Now it's relativistic, laser propagates through. And so that's what I want to investigate. That's what I did investigate in grad school. And my case was different. It's not that this experience was new or different. RIT is sort of well known and it's a thing. It's been a thing for many years. But what I did that was novel was that instead of most lasers focus down into a Gaussian spatial shape, and so you sort of have your Gaussian curve, looks fine, very nice in terms of math. what I did was I actually used orbital angular momentum, which instead of being a Gaussian shape, at the focus looks like a donut. And so it's dark, then you have a hot ring in the center, and then you've got a null point in the middle again. And so that now has orbital angular momentum. That's why they call it that, OAM beams. And it just sort of does different physics. And so I investigated how different it was. So I did OAM, RIT versus regular Gaussian relativistic reduced transparency, just to see the differences. So it was very cool.
Yeah, that actually sounds pretty interesting, especially since we're
Yeah.
going over quantum mechanics and special relativity in school right now.
Mhm.
So that's
Oh yeah, very cool. Yeah, yeah.
So
Um,
when you're talking about relativistic speed of the electron, it's to do with like the vibrations of it, right?
yeah, effectively the oscillations. Yeah,
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 okay.
yeah.
So how much faster is that than say like an electron that's not excited?
Right. So generally, the speeds of these plasmas are of order 10 to the 5, 10 to the 6 meters per second,
Okay.
which is wicked fast. Let's be honest.
But
That thing's moving. You need lasers to make things move that fast. You're not
yeah.
going to just push them that fast. Um, But now when we're getting relativistic speeds, we're talking closer to, appreciable amounts of the speed of light. So 10% the speed of light, 10, 10 to the 7,
Okay.
stuff like that. And so, and then you get closer and closer, it becomes harder and harder. It's a nonlinear process,
Yeah.
right? So you sort of cap out on the laser limit you have, and then you run into this, you almost run into an, upper limit is the wrong word, but once you become relativistic, you're transparent again. So now your laser just goes through, and your
Uh,
electrons don't absorb any more light because they've
yeah.
gotten fast enough. So it can you almost struggle to get, you're never going to get to C, but it can be hard to get them faster and faster and faster because you sort of reach this plateau where your laser just transmits through.
yeah.
Um,
So there's kind of this like sweet spot that you need it in then.
yeah, so sort of, yeah. So for numbers. When I was doing an experiment for my PhD, the transmission of light you can get before it's relativistically induced for a target can be, sub 5% light going through, depending on how thick your target is. But then if you make it thin enough, all of a sudden you can get 80, 90% transmission. And that's very exciting. That means there's a lot of signal transmitting through. But what that also means is that there's way less absorption into your whatever your target is. And
Yeah.
so if you only have now 10% of your light being absorbed into your electrons or your target in general, they're not going to accelerate as fast. Just you got less light and to do it.
You were talking about how copper is a target that's commonly used,
Yeah.
and you're talking about, obviously we're aiming these electrons at things, but I saw that they were specifically called ultra thin targets. What makes it an ultra, like why that name?
Yeah, yeah. So ultra thin. So my target that I use, I did use copper as an example here, but I actually never shot carbon. So I don't know why I used that example. But what I shot was this thing called 8CB, which is this. It's just this liquid crystal compound. And the reason that it was ultra thin, or that the reason we shot it, is because we could make it ultra thin. And so when I mean ultra thin, I mean that we can shoot things as thin as 10 nanometers in terms of laser direction. So 6, 10 millimeters in this direction in your sort of orthogonal plane, but in the laser direction, only 10 nanometers. And I say ultra thin because if we think of it in terms of, if we're now in the direction of the lasers, if let's just take it in chunks, 10 nanometer chunks. If that first bit becomes relativistic, well, then the next bit can now see lasers. Because as I said before, if your electrons are critically dense, it reflects off. And so if you just have this, what they call infinitely thick or quasi-infinitely thick target, your laser's never going to get to the end of it because you have to excite more and more and more electrons. And so your first chunk of your electrons can become relativistically transparent. Laser propagates a little bit further, and then same thing, so on and so forth. But eventually, if it's thick enough, a centimeter, you're never going to be intense enough to relativistically induce transparency for that whole centimeter. So,
Mhm.
but you can in 10 nanometers, you can in 20, you can in 30, 50 nanometers, depending on your laser intensity. You can sort of cheat for a given laser intensity. You can get to relativistically induced transparency if you have more intensity, more energy, or if you have a thinner target. And so we used the thinner target to get there. Sort of, but they work both ways. Yeah.
Mhm.
And what was the motivation behind this research? Do you have like a specific application in mind, or was it just
So my group's big research was in contrast enhancement plasma mirrors.
Mhm.
Um, and that's where we developed a lot of our liquid crystal technology. And then I just used that technology as a target. So what a contrast enhancement plasma mirror is, if we think of our laser pulses being on and off to induce, so if I said I shot a 300 terawatt laser. What that means is it's about 10 joules on target and a 30 frame per second pulse. Um, 30 frame per second is sort of it's such a small number, it's hard to sort of grasp what that means. So it's a millionth of a billionth of a second long. Um, wickedly fast. Nothing you can do electronically can go that fast. It has to be done, and it has to be created via light and lasers. But even that, still, I say 30 femtoseconds. There is going to be an on that sort of is what we call the pedestal, the pre-pulse, where you're sort of rising up into it, and then the peak of the pulse is 30 femtoseconds. But if you look at it on a log scale, you actually see like, oh, it started a little bit before. There's maybe a little bit of leakage or a little bit of ASC coming from the laser amplifiers that started a little bit early. And you might think, well, okay, uh, if I'm talking about 10 joules on target, if the ASC is 6 orders down to log scale, that's only 10 microjoules. That doesn't sound like a lot. But at these intensities, when we're shooting at 10 to the 21 watts per square centimeter, 6 orders down, therefore is 10 to the 15 watts per square centimeter. And this is target dependent, but roughly speaking, ionization will happen around 10 to the 12 to 10 to the 14 watts per square centimeter for generally any target. And so at 10 to the 15, that means you've already ionized. And so if you've already ionized something, well, then what happens is they kick out the electrons and the electrons move away. They're excited now. They spread out. And so you can get this sort of pre-expansion of your target. That might be very interesting. That might be very cool. But what that does mean is that it wasn't what you started with. And so if I had a 20 nanometer target that pre-expanded, well, when the peak of the pulse that got there, 10 picoseconds, 20 picoseconds, however much later, well, it doesn't see a 20 nanometer target anymore. It might see 22, might see 30, might see whatever the number is, 50 nanometer expanded target. That can be interesting. That can be what you focus on, but it's just not 20 nanometers. And so it can change the physics that you're looking for. So what you can do is that, okay, I shot on target 10 to the 20 watts per square centimeter. But if I put a plasma mirror in front, a contrast enhancing plasma mirror in front, so if I'm coming through a laser, it comes like this way, and then target, if I put here a plasma mirror, as it's focusing down, the intensity on your plasma mirror goes with the area of the target or of your laser, your spot size. And so you can get a larger spot size on this plasma mirror and reduce the intensity. So let's call it 10 to the 15 for simple numbers. 10 to the 15 watts per square centimeter, as I said, is enough to ionize your target and become critical dense and reflect off of it. Cool. Except for now, the stuff that was 6 orders down is only 10 to the 9, 10 to the 8. And so that stuff will transmit through because that's not enough to ionize. And so it'll transmit through your target as long as it's not opaque, it's not a sort of metal mirror. It'll transmit through and then it'll be lost to your actual target. So now you've effectively cleaned up your laser pulse in time. And so when you get to your actual target, you will still have, roughly speaking, the 10 joules on target. There's a little bit of efficiency in this ionization process, but you'll still have a reasonable amount of order same energy, so 5 joules, 6 joules, whatever it is, but it'll be a lot cleaner, so it won't have expanded. So if it's 20 nanometers, maybe it only expands to 21 instead of 41, instead of 81. And so it becomes more of what you intended to shoot. So that was a lot of what my research group is known for, is liquid crystal contrast enhancement plasma mirrors. And I just used them because we had them for targets.
Mhm.
And the way we did it is that the way we made our technology is that depending on how fast we make these films, excuse me, we can make them thicker or thinner. And so that's, as I said before, depending on what you're looking for in terms of science, changing the thickness can change the results. So it's sort of a nice control might be the wrong word, but a nice parameter scan where I can shoot thicker or thinner targets and figure out the effects on RIT.
Yeah, shifting topics a little bit. We saw that you worked at Aerojet Rocketdyne, and
Yeah,
I noticed that was like, of course, I'm gonna ask you some questions about that in a second, but
sure.
I thought it was quite interesting that you went from physics to mechanical engineering back to
Yeah,
physics and then aerospace engineering, which is
yeah,
like that's all kind of in the same realm, but it's
yeah.
you're still going
What
around.
happened?
Yeah,
Yeah,
exactly.
where did I get lost? No. So when I did undergrad, I did laser research. I did, quantifying materials, thicknesses, and refractive indices. Very cool. But as I said before, I didn't want a PhD because that was too long, and arguably is still too long. Um, but I wanted to separate myself, and Cal Poly, which is where I went to undergrad, didn't have a master's degree in physics. So sort of the next closest thing was some sort of engineering. Um, Aerospace engineering was an option. Mechanical engineering is an option. Civil, there's all these that types of options. But I always like to tinker, and so mechanical engineering was sort of the next best fit for me and my interests. So my master's degree was in mechanical engineering, but specifically finite element analysis, finite element modeling. And if you don't know what that is, it's sort of like things in general are complicated. Rockets are complicated, cars are complicated,
Yeah.
prosthetics are complicated. How would you, if you got a test and said, okay, I want you to model how much force a bridge can handle? Okay. Or how much force until a plane falls out of the sky? Okay. How would you do that? You'd make an assumption first. And so FEM, finite element modeling, is sort of that to the extreme. So what you do is you sort of model whatever you're looking at, your structure, your TV, your car, your plane, as a bunch of little mini springs. And so, okay, I don't know how to model a whole plane, but I do know how to model this point to this point as a spring. And if I make them close enough together, that's a reasonably good approximation. And if I model this point to this point, and then this point to this point, and so on and so forth, you can then build this sort of 3D structure full of springs, and you can push on this corner over here, and then it'll ripple and its way out. And you can calculate stresses and strains in structures, 3D structures this way. So,
Mhm.
so that was what my master's degree was on. Was I built a 3D human model or 3D FEM of a human knee and used it to predict to see the effects of what happens if you're walking without an ACL or with a damaged ACL. Does it change anything? Increase stresses? Do you change where the stresses are? Is it more of an area of the stretches? And so all these things can be then tied back to arthritis. And so you say, okay, because maybe, if I got in a car accident, if I'm not athletic and I got in a car accident, I don't work out at all. I may not need an ACL to live my day-to-day life. And every surgery, if you're going under, has an inherent risk. Something can go wrong. You could have a bad reaction. There's a whole bunch of complications that can happen if you have surgery. I'm not saying don't get surgery, but that is an inherent risk. What is the risk of not having the surgery? Am I more likely to develop arthritis in 15 years? Well, maybe if I'm 85, I don't care.
Yeah.
15 years, I won't be walking much anyways. But if I'm 25, 15 years, I'm still 40. I still have a long sort of physical life, active life ahead of me. And so that's sort of what I was looking at. Anyways, FEM is used a lot in a whole mess of industries. Actually, my first job interview after that was for Cobra, the golf company, and making golf clubs. And I actually didn't take that job because I got the job at Aerojet Rocketdyne first while they were on their annual week-long golf trip. And looking back now, that would have sounded really nice. But so I was at Aerojet Rocketdyne as a turbo analyst looking at turbo pumps, but in sort of this FEM sense. So sort of predict what the stresses and strains are in their turbo pumps. So some guy would design something and say, okay, it fits in this package. Some fluids guy would say, okay, this is the fluid flow of the liquid over them. And some temperature guy would say, all right, here's the temperature over that. And so then I would take it all, put it in a model and say, okay, looks great. Or, oh no, that we're gonna structurally fail over here, redo it. And so it'd be and then they'd redo it. And it would work for me, but then not for the fluids guy. Or it would work for me in the fluids, but it wouldn't actually fit anymore. Or it would work for everybody, but then the design upstream is like, oh, you scratch that, we're changing everything. It's like, oh crap. So it became a very iterative process. And rockets, it's probably, understatement of the year, are complicated. And so they take a long time to build, and it's a very iterative process. And so you need a team of people working on it. So that's why I went to Aerojet Rocketdyne to help build rockets. It was very interesting, very cool.
Mhm.
So
But
what
yeah,
kind of rockets were the things that you were working on used for?
yeah. So the rocket I was on, it didn't actually, I don't know if it ever got built in that there was a proposal call out from this company, the NASA, and they wanted to replace these Russian rockets with an American-made one. So Blue Origin, different company, and then Aerojet Rocketdyne, our company, were sort of bidding to compete for this proposal bill. And so we sort of had every whatever it was, 6 months, a year, progress report and say, okay, we've gotten this far along because rocket, as I say, they're complicated, take a long time to build. Um, at the beginning, everyone's got a great plan. It's going to work like this. It'll be cheap. It'll be this. It'll be the most efficient. You'll get there, in 5 years. Okay. But before they will accept the full bid and go with somebody, they just sort of will let people work a little bit at it and get, a quarter of the way there, however far along, to know, okay, actually, these people seem to be more fully developed in their plan versus these people, or these people have more historical backing, and I trust that they'll get there in the end because they're equal places. And so that was sort of what we were working on. It was trying to replace this old Russian rocket, Russian engine for NASA. So I left before it was finished, so I don't actually know if we won the bid, but yeah, so that's what I was working on. Was the turbo pumps for the AR-1 rocket? Yeah.
Mm, that's pretty cool.
Yeah, it was very cool looking back at it. It was very cool.
All right, so yeah, you worked at SLAC after that. I mean, obviously you're continuing to work at
Yeah,
SLAC.
yeah, they're not, yeah.
Well, I guess you're not really working at SLAC. You're working at
Yeah, not yeah. This week, there this month, I'm a UK employee, I guess. Yeah,
yeah.
I'm a Brit.
How are the lasers set up at SLAC? Because obviously you're working with a lot of lasers over there. And I remember I was actually at SLAC a couple years ago, and it just looked like
Nice.
this kind of metal grate with a bunch of holes in it, and people had all these like optics and mirrors sticking up from it. I'm like,
Yeah, yeah,
what? What is this? You know?
yeah.
Was that like at the end or is that at the start of the thing? And how not like a really in-depth of how it works, but
Sure, sure,
how
sure.
how does it get set up?
Yeah, yes, so it's everywhere. That's sort of what an optical table will look like. And you just basically start with mirror by mirror, and our laser sort of is born out of a commercial laser, and then we amplify it further because our laser is way more energetic than really any industrial laser needs. So it's not a thing that most companies will just like you can buy off the shelf. It's changing a little bit, but for the most part, all the things that we do are custom made. So we take an existing commercial product and then we then amplify it further with, in our case, in my case, TISAF laser, which is a very classic old school one. It's what your dad and what Bob worked on.
Yeah.
And it's the TISAF is the amplifying crystal, the amplifying media. So the way that works is that a separate laser will come through, it'll effectively charge up this titanium sapphire crystal. Then now it's in this excited state, this quasi-metastable state. And then your C laser, the thing you do your experiment with, will come through a little bit later and then extract out the energy from that crystal, and then it'll amplify it. So you sort of the way I phrase it to the people who aren't in the field is like you need lasers to make lasers more lasery. Is that you don't just turn on a laser and then make it intense. That's not how it works. You have a bunch of different lasers that come together in a specific way, whether it's a titanium sort of multi-pass amplification, an OPCPA, optical parametric pulse amplification. There's a bunch of different ways to do these amplifications, but they all require other lasers to make your laser more energetic, and to then be used for whatever your science is. Yeah, so what you saw here, or at SLAC probably, was that there was sort of the commercial product born over here, and then it worked its way through all these various amplification chains and compressing chains, such that it resulted in a laser that is not industry available, but is good enough for science. And so we sort of like that. And that's what the laser SRD group does, is that we take lasers that are quasi commercial available, and then we improve them, we use them, we modify them such that they become scientifically relevant, that can used, whether it's increased rep rate, pulse duration, change the color of the laser, whatever, what have you, and then we use it for our science experiment. So that's what that is, and that's sort of how lithography started with the semiconductor world, where at that time when it started, that wasn't a laser you could buy commercially available. A lot of research went into how to make the blue light that they use to cut your semiconductors, make that reasonably efficient, how to make it in the first place, and then how to make it efficient. Okay, now you made it efficiently. How do you control it? Okay, and then can you do it rep rated? And then once that was proven in the scientific academia world, where all right, these are all the steps you need to do, then your Samsungs, your Sonys, whoever who need these chips, are like, all right, we're gonna buy this and we're gonna make it industrially available and industrially reliable. And then that's when sort of the whole semiconductor world blew up because you need this lithography to make chips smaller and smaller and smaller.
I
Is
see.
that
Yeah.
something that happens quite a lot where you'll have like a breakthrough and then you'll resell it to industry as like a new method?
I wouldn't use the word quite a lot, but that is sort of how it's always worked historically, is
Yeah.
that something will have started in academia and it'll be gotten far enough along where we know this always works like this. And
Mhm.
then someone will come up with a great idea like lithography in terms of cutting semiconductors. It's like, oh, many academics, myself included, are very much interested in sort of pure science, research for research's sake, but may not have sort of that it factor or that clever idea to make money off of it. And that's where somebody else can come in through, say, "Oh, I really like what you do. Let's work together and we'll build a product out of that." And so a lot isn't the word I would use, but it is generally historically how that's worked.
Yeah.
Something will happen in academia and research communities, whether it's at a university like Stanford or sort of a research industry like Bell Labs, which is sort of a big one in the States back in the 80s, 90s, that produced just a lot of research for research sake, that then might get bought off and patents will be made that way. So that's how they can make the money is that, okay, you know, Samsung or whoever, Seagate, ASML makes these lithography things, and they'll just pay the patent for the original science. And so then Stanford or whoever will make money back on it.
Focusing in more on how to use these machines. I
Yeah.
noticed on your Stanford page that you said you wanted to make it more user friendly.
Yeah, yeah. So I am very selfish in that I want to make it user friendly so that I don't have to be called at 2 in the morning to come fix the laser. And so the way LCLS works is that generally speaking, the X-rays run 24/7 in 12-hour shifts. And there, as I said, there are 6 hutches, and most beam times are somewhere between 3 to 5 days or 3 to 5 shifts. And so what that could mean is that if you got five shifts of day shifts, you could be Monday through Friday at 6 a.m. to 6 p.m. Or you can get unlucky and you're Friday night, Saturday night, Sunday night, 6 p.m. to 6 a.m. And that's, yeah, it's not great. But that's when the science, this thing's always running. So the science is always happening. People always want it. And so what that means for me is I'm not the X-ray person, but I do the laser needed to make the science that the X-rays probe. And so I will set up the laser beforehand and then generally speaking, let them run with it. And SLAC will have instrument scientists that will help facilitate the experiment. So if you guys have this brilliant idea, your proposal gets accepted, you will work with our instrument scientists and with me on how to actually make your experiment happen. And then during your Sunday night at 2 a.m., you'll be working with them in the control room on actually doing the science. And then unfortunately at 2:30, something goes wrong and the laser stops working. It's devastating for you, more devastating for me because I get called at 2:30 in the morning. And then sometimes, depending on what it is, I can fix it remotely. And other times, if you've burned a crystal, if you burned a mirror, burned a grating, I have to come in and replace that. And so that's what I mean by making it more user friendly is I want to make it more foolproof. And so that you can use a laser. I don't have to get called at 2 in the morning. I would like to have a life and be able to do things on the weekend. And so that you can, and then even make them more impressive in terms of more energy, more shorter pulses, what have you, but still make it user friendly in that you can use it without fear of breaking. And so that would be great for me. Yeah.
So are they very like, for lack of a better term, fiddly? Do they break a lot? I mean, it sounds like it must for you to want to make it more user
Yeah,
friendly.
it depends on how hard you want to run it. And so if you want the absolute most energy, you want the absolute best compression, you want the best of this, that, and the other thing, it can be reasonably fiddly. But if you sort of say, okay, for numbers, if the best energy I can get out of my laser is 1.2 joules, very cool. Now, that might mean that usually means you can run a little bit lower, 90% lower, 85% lower, and that'll be stable. And so then what we provide to the users is, okay, we don't tell them we can do 1.2 joules. We tell them we can do 1 joule. Because if we tell them 1.2 and they come and whatever their science is needs that 1.2 and I can only get them 1.1, then they're going to be upset. They're going to complain. And sometimes rightfully so, sometimes not. But if they flew over from Britain and like, hey, it's Sunday night. I flew over for this experiment fix. I needed 1.2 joules and I'm only getting one. I can't get to the science I need. This is going to fail because of that. Like, you got to help me out. So, we try to under promise, over deliver. And that's what's going on with this EPAC laser at RAL. One, they're building it, but they're going to get to these points. And if I were to guess, they'll probably operate at a little bit lower threshold than whatever absolute peak performance is because users will come, they'll complain and they want this, that, and the other thing. And if that is as far as that laser can ever go, then, it's hard to operate at peak 24/7 for a whole time.
Yeah.
So yeah, I'm trying to make it user friendly in that it's more foolproof. So you guys can come to your crystal science, and then everybody's happy.
Okay.
Yeah, yeah.
Is
But
there
it's not easy. It's not easy. There's a lot of things that can go wrong. Damage, drifting, thermal things, if the power goes out at SLAC, then, what happens now? Type of stuff.
Is there a
Yeah.
backup generator if power does go out?
Uh, um,
They're like
there's emergency
safe
generators.
method or
If the power goes out, the experiment's sort of shot, but there are emergency generators to try and make sure there's not like catastrophic failures.
yeah.
So like a lot of the accelerator is cooled with helium cooled, and so they'll have like backup generators to make sure that you don't lose all the helium into the atmosphere, because
Yeah.
it's expensive and they use a lot of it.
So at the beginning, you said you were working with matter under extreme conditions, right?
Mhm. Yeah, yeah.
What exactly warrants that name? Like what are the conditions that have to be met for you to be calling a project, for it to be in that division of science?
Sure. Yeah. There's not really like a hard definition where like, oh, over 25 miles an hour you're speeding. It's not like that. It's just that generally speaking, you're hot enough and you're dense enough such that you're in this plasma regime. And so broadly speaking, the plasmas that we get to are sort of warm dense matter, which is temperatures and pressures seen on the surface of the sun, the internals of Jupiter, of Earth. You get to those temperatures and pressures that are at the molten core that you can't actually ever get to, from mechanical means. You're not going to drill to the middle of the Earth. Just
Yeah.
not realistic. So what you do is you take a laser that can heat up and compress a target enough such that in, a 10 micron, 100 micron space, it's as hot, it's as dense as the middle of the Earth, as the core of Jupiter. And so that's there's the extreme conditions because they of course they exist, of course they do, but the sun's famously far. You're never going to get there. It's hard to probe it. How are you going to send X-rays to the sun and get any information out? How are you going to get into the middle of Jupiter? How are you going to get into the middle of the Earth? And so we make these conditions that obviously exist and are relevant in terms of science case to study, but you can't do in any other fashion. You can't just take a piston and keep pushing it harder and harder and harder. Eventually, you sort of reach a limit of how hard you can mechanically push something.
For specifically matter under extreme conditions, what applications would that have for maybe possibly like helping design new tech? I mean, obviously it's not going to be that specifically,
Sure.
but like just
Yeah.
just in general that branch of science,
Yeah.
what
So the big one, the buzzword one is fusion. Um,
okay.
And so, um, green energy can come in many ways. Hydro, wind, solar, they already sort of exist. Fission power plants are where you take an atom and you split it apart. And that has existed, they've got one in California, 3 Mile Island, Chernobyl. These are all, infamous examples of them. But fusion is the opposite, where you crash two hydrogens together and make helium, and then produce just buckets of energy. Uh, it happens in the sun. That's what powers the sun. It's hard to do. You can't do it mechanically. You can't just push two hydrogens together efficiently and make fusion happen. You can in terms of bombs. Sure, a fusion bomb exists, but it's not exactly an efficient process in terms of extracting energy out in turn for, running your TV at night. The goal is to now do fusion with lasers. So you can press these hydrogen targets such that they become hot enough, they become dense enough, where then they fuse together and they kick off and ignite. Ignition. You get ignition, and you've now produced more energy out than you've put in. That's what fusion is. Fusion generates energy, and if you get the balances right, where you can put in, X amount of energy and get 2X out, well, then now maybe you can use that extra X left over from the interaction to then you can capture it and use it to power all the lights in the city, wherever, hospitals, all that. So that's the big one is fusion. And there's been a lot of fusion research for the past 20, 30 years at Livermore in the Bay Area. And there's sort of a renewed vigor in the past 5, 10 years, and that they've reached a level of ignition, meaning they've gotten more energy out than the laser energy in. So various levels of that ignition threshold have been reached. So it's excited people. And now the next threshold is the final threshold is to sort of get more energy out of the interaction than wall plug energy. So every laser takes energy to run the laser. Okay, sure. Maybe they've shown that they can get more energy out than the laser energy put in. But how much energy did the laser need to be generated? And so that's that threshold needed to reach. Can you get more energy out than wall plug energy in? And once that is sort of, quasi renewable energy, um, you still have to make the targets and all that. There's a whole host of problems. But that's sort of what the big goal is of fusion is have a renewable power plant, renewable energy source, a clean energy source. Or fission, you get leftover nuclear waste that you sort of just bury underwater, which is, not great. Um, but this fusion plant won't have these sort of nuclear waste subsidiaries. And then generally, you can also just, if you're interested in relativistic plasmas, that's not really a fusion type plasma. That's too energetic. And that'd be more looking at sort of science sake or something like magnetic recombination. So like the sun, if you've ever seen sort of these pictures of the sun, these amazing chronographs, you can see these arches of sort of solar flares. And what can happen is that you have this arch and then this arch, and then all of a sudden arch A and B sort of break together and then they reform. And when they reform, out comes this big solar flare and this solar, and if it's flying at Earth, it takes out all the satellites, civilizations in the Stone Age again. That's terrible. We don't want that. We can't prevent that. But what we're trying to do is study and understand this thing called what they call magnetic recombination, and that's more a higher energy plasma state than would happen in fusion plasmas. Or that's a thing lasers can be used for. They don't necessarily do that at SLAC, but yeah. NIF with the National Ignition Facility in Livermore, amazing laser, huge laser. It's a very old laser, and it's using technology 20 years old, 30 years old, and it's state of the art from its time, and of course it is, except for the fact that it's just not the most efficient. And so there are a lot of people who are looking at making more efficient lasers, exactly what you're talking about. How can I make, just from a laser point of view, how can I get the same energy out with less wall plug energy in? And so it's a sort of it's one of the big ways to get closer to this ignition goal. Because eventually you can only get so much energy out of your target. If you go from your quantum mechanics, your certain amount of mass only has so much energy, and so you
Yeah.
can only get so much out. And so a way to make that efficiency, that ratio better for you is that the laser energy needed is less. But yeah. So you're totally right. And there are a lot of companies who are working to make a lot faster and a lot more efficient lasers for the same energy out, as you put it.
So is
Yeah,
that,
go for
okay.
it.
I was just gonna say, so is that something that would help pretty much the entire laser industry if we found out how to make them run more efficiently? Like
Yeah.
not just about cost effectiveness and fusion and getting more energy out than what we put in, but would that help us? Like if we can make it more efficient, then could we also, maybe put more power in because they're more efficient, then we could easily
Yeah,
get
100%.
stronger
Yeah.
lasers and stuff
Yeah,
like
yeah.
that.
Yep. And, so you can run into things like laser damage threshold.
Mhm.
So it's not quite the same as ionization, but ionization is like an extreme example of it. If you ionize something, it's damaged. But you can also damage something without ionizing it. And so there is sort of a material cap on what can handle, like how much energy, how much fluence you can put on a given thing. But people are researching that on how to make that better or higher that laser damage threshold. How to improve the you can sort of tweak the laser and these all these lasers I'm talking about are pulsed, meaning that they're only on for a certain amount of time. If you make them longer in time, generally speaking, the damage threshold goes up. And so if you can do the same science with a longer pulse or the same, and then be science, same industry application with a longer pulse, and that'll generally speaking help your damage threshold so you can make them smaller and more compact. All this is 100% into that. Then there are other things. If you made it more efficient, you can do things. We don't do this at SLAC, but other people definitely do. They're looking at trying to make um, a laser source for proton therapy for cancer treatment. And so proton therapy exists. It's very cool. It's very interesting work. Where now instead of chemo, you can have sort of targeted cancer attacking devices where you have this proton beam directly aimed at your tumor and can destroy it that way. And generally speaking, these exist and they're big and they're expensive to run, but they're not laser based. And the notion is, okay, well, can I build a laser that is smaller, a whole compact package that can provide the same amount of proton energy and flux such that you can make it cheaper, more easily available, and have it be more widespread so that you can try and, help out all these people who've got cancer who maybe can't access proton therapy because they only exist in, however many places in the world.
Or okay, so I know we're coming up on our time here, and I want to be respectful of that. But I did actually have one last
Sure.
question that I thought of when you were talking about how when you ionize something, it's damaged, right?
Yeah, yeah.
But you said that that's an extreme case of it. So
Mhm.
how can something how else on the atomic scale can it be damaged? Because wouldn't that like at least from my current understanding of quantum mechanics and just atomic physics in general,
Mm.
isn't that just blowing the electron into like
I mean,
another
you can melt something,
or
right? So you can just like heat it up to the point where you've melted the surface,
okay.
and that's not necessarily ionization.
Yeah.
And so, but it would damage it. Like, so is a lot of things like a lot of mirrors, for example, are spec'd at a flatness. And so a common metric is lambda by 10. And what that means is if you look at a mirror and you can sort of look at it atomically, it'll be wavy at the lambda by 10. So if it's 800 nanometers, it'll be an 8 nanometer waviness.
Mhm.
Okay, cool. But if I've melted the surface, well, it's no longer 8 nanometers. It'll be whatever it is. It'll be ruffled, it'll be gross, it won't reflect well, and so it'll be damaged. And so that's one way you can just melt it. Um,
Yeah, okay, exactly six. Okay, well, we appreciate you taking the time out of your day
yeah,
to talk to us. That was really
no
nice.
worries.
We've been looking forward to this, and
Mhm.
yeah, I thought we covered some pretty interesting topics.
Yeah, yeah. I'm glad I can help, guys. Thanks for having me on. I appreciate it.
Yeah, definitely.
Yeah, it was good
All
fun.
right, everyone. I'll see you in the
Yeah.
next episode next Monday.
Yeah.
Thank you, everyone.